So today we want to finish up our trigonometric substitution talk. And it comes down to this. We need to know which products of powers of trig functions are not substitutions. And then we need to learn how to integrate those because they're the only ones that we're going to care about in the context of trigonometric substitution. Because if our theta integral is a substitution integral, then our x integral was also a substitution integral. We should stop trig sub, go back and do our regular sub. So we need to know what products of powers of trig functions are not substitutions. Because that's the most common thing to happen when you're doing a trig sub. Products of sines and cosines, products of secants and tangents. To that end, we've already solved the sines and cosines. If m or n is odd, then that one is your dw. If m is odd, cosine is your dw. If n is odd, then sine is your dw. Because remember, the substitution question is all about what's going to be my dw. So if m is odd, so if m or n is odd, it's a substitution. Say one factor to be the dw, convert the rest. Notice I wrote it in terms of dw because that's what really matters in the substitution. So one cosine is going to be the dw, and the rest of the cosines can be replaced with sines. So if n is odd, like we have 5 factors of sine, one of them is going to be the dw, the other 4 could be converted to cosine. It's a little more complicated when we start with secants and tangents, because the derivative of tangent is secant squared, and the derivative of secant is secant tangent. So each of those derivatives need two factors. So that changes how we think about it a little. Oh, I forgot to say. So if m and n are both even, that's when we do not have a substitution problem. So here is the first product of powers of trig functions that we have to know because it's not substitution. If m and n are even. Our way in to integrate this is to use a double angle identity for cosine squared. And so we can summarize m and n are even as even powers of cosine. That is the first category of not substitution. We can take the even powers of sine and convert them to cosine, and so we just have to worry about even powers of cosine. Moreover, we know what to do with these even powers of cosine. We trade cosine squared with a half plus a half cosine of 2. I kept forgetting to say the x. So the strategy here is to use cosine squared x is a 1/2 plus a half cosine of 2x. So that's our first category that we have to deal with. We might be doing trig substitution and come up with sine to the fourth cosine squared. That's not a substitution, and we need to start converting those even powers of cosines to cosine of even number times x. So our cosines and sines sorted, all sorted out. The one we have left to sort out is secants and tangents. So let's review the substitutions that we have here. Here's our toolbox for secants and tangents. If I substitute W equals tangent theta, or tangent X, then for dW, this is the thing that we need. I need secant squared X, but any other secants have to be converted into tangents. Any other secants have to be converted into tangents, but they only get converted in pairs. Otherwise, for our purposes. Otherwise, it just gets too messy because we start introducing square roots. So the other secants get replaced with tangents. So if I have 4 secants, I can substitute tangents. 2 of them to be the dW, and the other 2 can be converted into tangents. If I have 5 secants, I can't do tangent because I need 2 to be the dW. 3 don't convert to tangent without a square root. And that's what we're trying to avoid. So we can see that this substitution works if we have an even number of secants. So we have substitution if we have an even power of secant. Note that this is the case even if the tangents aren't there at all. Because if we have the integral of secant squared, that's just tangent. So that counts. Technically not a substitution problem, it's just one that we know. But even if we had secant to the 4th, no tangents at all, 2 of them can be the dW, the other 2 become tangent squared plus 1. And so I integrate W squared plus 1 dW. So the tangents don't actually have to be there to make that our substitution. It's one of the tricky things about this particular line of thinking. That's why our thinking is based on the dW, not the W. If I have the integral of secant to the 4th, I'm still making the substitution W equals tangent. Because the substitution really starts here at the dW. That's where we make our decision. Even powers of secant, no problem. That means we need to look at odd powers of secant. Let's see what we need for W equals secant X. If W is secant X, then dW is secant X, tangent X, the X. And any remaining tangents can get converted to secants. So tangent squared can become secant squared minus 1. So the decision comes down to secant tangent. Then I have to have an even number of tangents left over that I can convert to secants. If there's an even power of secants, then we're not even going to worry about making the substitution secant. There are conditions under which that'd be perfectly acceptable. But if there's an even power of secants, we don't care because we've already got a way to integrate any even power of secant. Tangents or no tangents. So we're considering odd powers of secant, and we can see what we need. If we have an odd power of secant, we're going to need at least one copy of tangent to make this substitution. And then we have to have an even number after we save 1 to be the dw. So if we have an odd power of secant and an odd power of tangent, then we can make the substitution. Spelled power wrong. So this is the substitution that we can make a substitution if we have an odd power of secant and an odd power of tangent. To make the substitution secant, I need a secant and tangent. One tangent to be to contribute to the dw. The remaining even power of tangent can convert to secant. And now we're left with one last case. This one had an and in it. So the last case is odd powers of secants, even powers of tangents. That's the only thing what's left over. Let's suppose we have an odd power of secant and an even power of tangent. So neither of our substitutions are going to work in this case. If I try to make w equal tangent x, then dw is secant squared x dx. And any remaining secants will have to become tangents. Secant squared is tangent squared plus 1. But I can't break this integral up in a nice way. Tangents are no problem. Those can all be just W's, but this secant cubed, I can save 2 factors of the secant to be the dW. But I won't be able to get those secants and tangents without radicals. And that's what we're trying to avoid. This does not mean that it's impossible. It just means that it's kind of inconvenient. If we pick the right power of tangent, then I could have a square root of W squared plus 1. If I have one factor, oh, I have to have an even power of tangent. There might be something that we can do, but it's not going to be a nice straightforward substitution, which calls for something else. Also notice that our substitution secant is not going to work because of that even power of tangent. So if I try the substitution W equals secant x, then dW is secant x tangent x, the x. And any tangents will be replaced with the secant squared x minus 1. It's okay if we're making the substitution W equals secant, doesn't really matter what powers of secant we have, they can all just become W's. So throwing in more secants down here, that just makes more W, that's fine. But then when we try to break apart this integral, we end up with, I need a secant and a tangent to be the dx. So I'm going to keep 2 of these secants because I got to separate 1 to be the dW. I also need 1 factor of tangent to be the dW. And then that leaves 3 factors of tangent. And then we have the same issue with this tangent cube. We can convert tangent squared. Tangent cube is going to need radicals. So we can summarize. So this is the case where we do not get to do substitutions. This is a product of powers of trig functions. That is not a substitution problem. This is odd powers of secant paired with even powers of tangent. Since even powers of tangent are just even powers of secant, we can write this as odd powers of secants without tangents. So there are our 2 cases of product of powers of trig functions that are not substitutions. Even powers of cosine and odd powers of secant without tangent. So now we need to learn what integrals, now we know what integrals we need to learn so that we can complete trigonometric substitution. Is everybody okay? Uh-huh. Correct. Oh, yeah. So if we have integral of, that's a great question. I just kind of like talk my way through it. Let's suppose we have secant to the fourth. We're going to make the substitution. We have an even powered secant, and we know that the substitution that will work is tangent, because this secant to the fourth has enough room for a secant squared to be the dw, and it leaves two secants to turn into tangents. That's where we're going to get our tangents from. So what we're going to say is w is equal to tangent, even though it's not there. dw is secant squared x into x. And then the other secant squared is where we're going to get some tangents. So I'm going to split the secants two at a time. And I'll have the integral of secant squared times secant squared. And that blue secant squared is going to turn into a tangent squared plus 1. And there is where we get our tangents. So now that tangent squared plus 1 we can write as w squared plus 1. And the secant squared x dx is all just dw. This is a little bit strange because we're making a substitution. W is going to be something that we don't actually see in our integral. But that's because we're new. You see that secant to the fourth, so we don't see all those tangents sitting inside that secant to the fourth. So we make the substitution w equals tangent x, even though it's not listed in our integral, because we see those two tangents sitting in the two secants. Questions? I should complete at least one problem today. Is everybody okay? Of course, it's Friday. You like all complicated thing. Yes, got it. Who's on this on Monday? Nope, no problem. No questions. Only 5 minutes left of class, and it's Friday. I'll sort it out over the weekend. So we know how to integrate even powers of cosine. It's not substitution, but we've got our double angle identity for that. For these odd powers of secants, remember if we have even tangents, those just become odd powers of secants. But if I got secant x, all we have to know now is that secant of x is natural log of the absolute value of secant x plus tangent x plus c. I did not explain how I got there. There's no trick to it. It's just a simple trick, but it is one of the 3 great tricks of mathematics. Multiply by 1, add 0, change your variable. Probably not a change your variables thing, since that's what this whole topic is about. Once we establish secant to the first x, that integral, that odd power of secant, we can use that in subsequent odd powers of secant. After that, it's all parts. So the next thing that we need to learn how to do is integrate secant cubed x, but it's parts. Remember when thinking about parts, the primary question in parts is that dv must be something that you can integrate. If I have 3 factors of secant, I could make the dv 1 factor of secant, but then the v is going to be natural log of secant x plus tangent x. That's going to be in my secondary integral. And I do not like that problem, that prospect. But if I make the dv 2 factors of secant, then v is just tangent. And that seems much more reasonable. Any questions? So here's your Blu-ray bonus problems for the weekend. Figure out how the integral of secant x is the natural log of secant x plus tangent x. Take the derivative, that'd be the way in, figure out what happened. And then integrate secant cubed x using that secant x and figure out how to distribute the parts to make it work. Then take one step further and integrate secant to the 5th x also with parts. All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Have a good weekend, and thanks for playing.